All right, so by popular demand, this is 4.2, number 19. Sorry, it took a while for me to get this up. Okay, so this is generally speaking one of the hardest problems in this section because reduction of order usually is only taught using homogeneous differential equations. But you can actually derive the entire process for non-homogeneous, which is this. So recall that if we create a second solution using reduction of order, we're going to assume that the second solution is u of x times y sub 1 of x. And if you forgive my notation, I am actually going to go ahead and stop using of x here. I'm going to replace y sub 1 with e to the x. And then what we're going to do is plug this y sub 2 into our differential equation to see what are the conditions on u. So y sub 2 prime is going to be u prime e to the x plus u e to the x. And actually, I'm going to factor out an e to the x, so it's just u prime plus u e to the x. And then y sub 2 double prime is going to be, again, derivative of the first, which is u double prime plus u prime, times the second plus the first, u prime plus u, times the derivative of the second, which is still e to the x. And I'm going to factor an e to the x out to get u double prime plus 2u prime plus u times e to the x. Okay, so I'm going to take those two derivatives and y sub 2 itself and plug those into our differential equation. So y sub 2 double prime minus 3y sub 2 prime plus 2y sub 2 is going to be, well, let's see, y sub 2 double prime is, again, I'll write it out front, e to the x, u double prime plus 2u prime plus u, minus 3 times y sub 2 prime, which is just e to the x, times u prime plus u. And then finally, plus 2y sub 2, that is. So that's 2u e to the x. What I'm going to do is collect like terms with respect to u prime, and u double prime. That is, I have an e to the x u double prime, and as far as attached to u primes, I have a 2 e to the x attached to that u prime, and I have a negative 3 e to the x attached to this u prime. And then finally attached to u would be e to the x, a minus 3 e to the x, and finally plus 2 e to the x. And this is attached to u. Now, if you note, this statement is just like our differential equation. And in fact, we were told that when we plug e to the x into that differential equation, it solves the homogeneous version of the differential equation. That is, plugging in e to the x will turn this entire statement here into 0. So let's go ahead and say that this, therefore, must be equal to e to the x, u double prime. Let's see, 2 e to the x minus e to the x is a minus e to the x, u prime. And that's it. And we want that to equal 5e to the 3x. I haven't done anything incredible here. I've just plugged things in. So let's go ahead and divide, setting these two to equal each other, which they are, but I'm just going to go ahead and showcase it. E to the x u double prime minus e to the x u prime is equal to 5 e to the 3x. I'm going to divide everything by e to the x. So u double prime minus u prime is equal to 5 e to the 2x. And now I'm going to use, here's the step, reduction of order to reduce this down to a first order differential equation. So I'm going to let w equal u prime, which will imply that w prime is equal to u double prime. And so when you do that, our differential equation becomes w prime minus w is equal to 5e to the 2x. And now I can solve this linear differential equation by finding the integrating factor, mu. Mu is equal to e to the negative, actually it's e to the integral of p of x dx. And the p of x is negative 1. So it's e to the integral of negative 1 dx. Or in other words, e to the negative x. That's what mu is. So therefore, that differential equation right here, okay, the left-hand side is actually a compressed form of the derivative with respect to x of mu times w. In other words, if I were to take the derivative, oh, by the way, that is true if I have multiplied everything by mu. So let's multiply everything by mu. We'd get mu w prime minus mu w is equal to 5 e to the 2x mu. Okay, and if you take a look at that left-hand side, that is the derivative of w times mu minus mu times, oh, no, that's right. Anyway, sorry, it's the derivative of w times mu plus the derivative of mu times w. So actually, that negative mu actually is, if you take a look at mu here, mu is e to the negative x, so the derivative of mu would be negative e to the negative x, which is negative mu. So that is technically the derivative of mu. It's kind of interesting. And so we want this to equal 5e to the 2x mu. We've already stated what mu is, so that's e to the negative x, so that's 5e to the x. And now you integrate both sides. So you'll get that mu w is equal to 5e to the x, technically plus a constant here. But as we know, that constant will actually disappear. I'll keep it in there just to showcase it. Okay. And then remember, mu was e to the negative x. And so what I'm going to do is multiply, oops, I don't know why I wrote x to the x. I'm going to multiply both sides by e to the x, so you get that w is 5e to the 2x plus c1 e to the x. And again, that constant is not necessary. And you're about to see why. So remember, w is actually equal to u prime. So I'm going to go ahead and integrate both sides to find out what u of x is. Integrate that side, you will get that 5 halves e to the 2x plus c1 e to the x plus technically ac2. So now you will go ahead and find out what y sub 2. Oh, and actually, I should mention this. I don't know why I didn't mention this from the get-go. When you're finding this solution, you're not actually finding, oh, that was miserable on my part. I'm so sorry. You're not actually finding y sub 2 this entire time. You're finding y sub p because you're solving a non-homogeneous differential equation, right? So you're actually this entire time solving y sub p. So I don't want to re-record this and fix that. I'm just going to tell you that this entire time we were finding y sub p. Y sub p is equal to a function times y sub 1. Okay, so anyhow, that's we're about to, I don't know why that of x is gone. But anyhow, so when we get down here, it's not going to be a y sub 2 is equal to, it's a y sub p, our particular solution. And actually, it's really going to just be y because I'm leaving all the constants in here. Because as we talked about in class with reduction of order, those constants will regenerate your y sub 1. They'll create your y sub 2. And in this case, they'll also create your y sub p. It's kind of a cool process. So your really full solution is equal to u of x times y1 of x. And if you take a look at this, u of x is, again, this stuff here. And y sub 1, if you recall, is e to the x. So if I multiply all that stuff by e to the x, I get the following. 5 halves e to the 3x plus c1 e to the 2x plus c2 e to the x. Now, as I said, if you leave the constants of integration in there, you regenerate your c1. And keeping all our constants in there, we actually create the y sub 2. So we regenerate y sub 1, we create our y sub 2, and on top of all that, we get our y sub p. So that is actually the entire solution. A very, very good example of using the reduction of order method to regenerate a full solution, y of x, for a non-homogeneous differential equation, given only a single solution to a homogeneous differential equation. So very, very cool.